Welcome to Semester 3 Statistics. Today we are diving into one of the most fundamental concepts in all of data science and statistics, the standard error. We will build this from the ground up, so do not worry if it sounds intimidating right now. By the end of this video, you will understand exactly what it is and why it matters. Let us start with a simple thought experiment. Imagine you want to find the average height of all students at Delhi University. You cannot measure everyone, so you pick a random group of 30 students. If your friend picks a different random group of 30, their average will probably be slightly different from yours. If 100 people did this, we would have 100 different averages bouncing around the true university average. The standard error is simply a measurement of how much those sample averages bounce around. It tells us how much we can trust our single sample. Now that we have the intuition, let us formalize this. In statistics, any number calculated from your sample, like that average height, is called a statistic. Next, imagine a massive imaginary collection of all possible averages you would get if you repeated your experiment infinitely many times. We call this the sampling distribution. The standard error is defined simply as the standard deviation of this imaginary sampling distribution. It measures the precision of your estimator, representing the typical mistake you expect to make when using a small sample to guess a big population's secret number. This brings us to the mathematical formula for the standard error of the sample mean. Conceptually, this formula compares the natural variation in the population to the size of your sample. The symbol sigma represents the true population standard deviation, measured in the original units of your data. The letter n is your sample size, which is just the number of observations. Notice that n is in the denominator under a square root. This means that as your sample size gets larger, the standard error shrinks. A larger sample gives you a much more precise estimate. Before we move on, let us see this with a concrete example. A factory produces light bulbs with a known population standard deviation of 120 hours. An inspector takes a random sample of 36 bulbs. What is the standard error of the sample mean? We are given the true population standard deviation and the sample size. Because the population spread is known, we use our exact theoretical formula. We place 120 in the numerator and the square root of 36 in the denominator. This sets up the arithmetic we need to solve. Continuing with our calculation, we evaluate the denominator. The square root of 36 is exactly 6. Now, we perform the simple division of 120 by 6, which gives us exactly 20. The standard error of the sample mean is 20 hours. Physically, this means that if the inspector repeatedly took samples of 36 light bulbs, the average lifespans calculated from those samples would typically miss the true factory average by about 20 hours. Now that we have used this formula, let us understand exactly where it comes from, mathematically. We start with the fundamental definition of the sample mean, denoted as x bar. To calculate it, we add up every single observation in our sample, from the first to the last, and then divide by the total number of observations, n. To find how much this sample mean varies from one sample to another, we need to calculate its variance. We take the entire formula for the sample mean and place it inside the variance function. This sets up the mathematical operation we need to perform to find the spread of our fraction. Understanding this setup is the crucial first step in our proof. Moving forward with our derivation, we apply a fundamental rule of variance. When you pull a constant multiplier out of the variance function, you must square it. So the fraction 1 over n becomes 1 over n squared when pulled outside the variance operator. Next, we look at the sum of the random variables. Because our sample observations are chosen randomly and independently from the population, the variance of their total sum is simply the sum of their individual variances. Since we are adding up n total observations and each one has a variance of sigma squared, the total variance of the sum is exactly n times sigma squared. This simplifies our complex sum into a single manageable term. We are now ready to find our final result for the derivation. We substitute the sum's variance back into our main equation. Now we can simplify this mathematical fraction by cancelling out common terms. We divide out one copy of the sample size n from both the numerator and the denominator. This leaves us with the variance of the sample mean, which is simply the population variance divided by the sample size. Finally, because the standard error is defined as the standard deviation of the statistic, we take the square root of this variance result. This perfectly yields a beautiful final formula, sigma divided by the square root of n. You have now proven exactly why the formula works. So we have proven that this formula holds. This brings us to a powerful visual representation. What you are looking at is a comparison between the raw population and the sampling distribution. The wide curve represents the raw population, showing a lot of natural variation spread out by sigma. The tall, narrow curve inside it is the sampling distribution of the mean. Notice how much tighter it is? This visual tightening is exactly what dividing by the square root of n achieves. It proves why taking a sample average is such a powerful tool for finding the truth. This visual leads us to an important practical question. In the real world, we almost never know the true population standard deviation. If we do not know the population mean, we certainly do not know its exact spread. Therefore, we must estimate the standard error using the standard deviation calculated from our own sample, denoted by the letter S. We simply replace the unknown population parameter sigma with our known sample statistic S. This estimated standard error is what we actually use in practice to build confidence intervals and test hypotheses. Let us apply this estimated formula to a real scenario. A researcher picks 64 apples at random to find their average weight. She finds a sample mean of 150 grams and a sample standard deviation of 16 grams. Because the true population spread of all apples is a mystery, we must use the estimated standard error formula. We plug in our known values. The sample standard deviation of 16 goes in the numerator and the square root of our sample size 64 goes in the denominator. Continuing our calculation, we evaluate the square root of 64, which is exactly 8. We then perform the final division of 16 by 8, giving us exactly 2 grams. This estimated standard error tells the researcher that her sample mean of 150 grams is likely within a few grams of the true orchard average. If she wants to build a rough 95% confidence interval, she would go about 2 standard errors above and below her sample mean, giving a highly confident range of 146 to 154 grams. Now that we have calculated it, why does this matter so much? The concept of standard error is the absolute backbone of all modern statistical inference. Without it, we would have a sample average, but absolutely no idea if we could trust it. When you see a political poll with a margin of error of plus or minus 3%, that margin is directly calculated from the standard error. It allows doctors to know if a new medicine actually works or if the results were just a lucky random sample. Let us wrap up what we have learned today. The standard error is the standard deviation of a statistic's sampling distribution. It measures how much your sample estimate naturally fluctuates. We calculate it by dividing the standard deviation by the square root of the sample size, estimating it with sample data when the true population spread is unknown. Ultimately, remember this. A smaller standard error means your sample estimate is sharper, more precise, and much closer to the hidden truth of the population. You have now mastered the foundation of sampling distributions.